So, we are at Nuclear Chemistry Part 3, and one of my most favorite topics, radioisotope half-lives. And for you in New York State, this is reference table N, and it gives you the half-lives of about 30 different radioisotopes. Okay? It gives you the decay mode and the half-lives. Now, these half-lives, it just means how long it takes for half of the radioactive sample to go non-radioactive. That's what a half-life would be. The other thing about these half-lives, you can't change them. So whatever the half-life is, that's how long it takes. And that's kind of bad news, because if we were able to shorten the half-lives, well, then the radioactivity we could do away with, but we can't. So whatever the half-life is, that's how long half of it takes for the radioactive element to go non-radioactive. Okay? Now, I've got a few little tricks, and this really pertains to our area of the country also. What we are going to do is we are going to do some questions from the packet. Now, I know a lot of you don't have this packet, but this is called Half-Life Quiz. And the first one we're going to do, I'm going to write down, and it has a story behind it. So, first of all, it says 80 grams of iodine-131 decay to 2.5 grams. And they want to know how long it takes. But I have to tell you about this iodine-131. Remember, every element has at least 3 isotopes, and one is normally radioactive. Well, iodine-131 is radioactive. And Chernobyl, which you should all see the miniseries, it was great. Chernobyl, Reactor 4 blew in the spring of 1986. This is a picture taken from a helicopter of where Reactor 4 was located. Now, I took high school kids to Europe, and we would always go behind the Iron Curtain for one country. And I did this for about 15 years, but we did go to Europe in 1986, and we did go behind the Iron Curtain. We went to Czechoslovakia. And I will tell you, when we went to Czechoslovakia in July, people were still taking iodine tablets, which I'll explain in a minute. We couldn't drink any milk, no fresh fruits or vegetables. It was all canned. We only stayed a day or two in Czechoslovakia and then went back to Western Europe. Now, iodine-131, if you look on your chart, has a half-life of 8 days. But in a nuclear explosion or in an accident like Chernobyl, iodine-131 is released into the atmosphere. Now, even though it only has a half-life of 8 days, it's a gas. And this gas is super deadly, because if you breathe it in, it all goes to your thyroid gland. Your thyroid gland normally absorbs iodine from foods that you eat. But this would be radioactive iodine that you would be absorbing. And obviously, it is a cancer maker. So people, what they did is they popped tons of regular iodine pills to fill up their thyroid gland So if they came in contact with any gaseous iodine-131, it wouldn't be absorbed by your thyroid gland. That's why all those people were popping iodine pills. Now, I told you before, radiation is weird because if you breathe in radioactive iodine-131, it could give you cancer, but iodine-131 is used in nuclear medicine. They inject iodine-131 into your body if you have a problem with your thyroid gland, and then they can see if your thyroid gland is functioning properly. Now, here's the deal. If you are injected by a radioisotope like iodine-131, you want two things. You want a very quick half-life, which this is 8 days, and you want quick elimination from the body. Those two things you want for a radioisotope. So that's the background about radioactive iodine-131. Pretty wild stuff. Now, how you solve this first question. Here's my method. They give you, it starts out with 80 grams. You go to 2.5 grams. So if they start out with grams and they give you the end up product grams, well, this is the way I tell my students to do it. Use your fingers. And the first thing you always have to find, I don't care what type of half-life problem it is, the first thing you always have to find is how many half-lives did it go through. First thing. So look, we start at 80, we're going down to 2.5. So the first half-life knocks it down to 40, 20, 10, 5, 2.5. So the first thing we know is we have 5 half-lives. Okay, that's the first thing. And you can do this on your fingers, like I said, if they give you grams and end up with grams. Now, all we need to do is we need to know how much one half-life is. One half-life is 8 days. So 5 times 8 equals, and there's your answer. So in order to knock down the sample 5 half-lives, it'll take 40 days to do. Okay? So we will talk more about radioactive iodine when we have our little talk about Chernobyl. All right, so if it gives you grams, both starting out and ending, figure out the half-lives on your fingers, and then you simply multiply it by what the half-life is. Okay? That one's done. Now, the next one is even cooler. Okay? The next one is used to date things that were living. So this is what we're going to be talking about. Carbon-14, that's the radioactive carbon. Now, carbon-12 is normal, and that's what's in CO2, but there is some carbon-14 in the CO2, okay? And what they did is the half-life of carbon-14 is 5,715 years. So the half equals 5,715 years. Now, there was this person that they found, I think it was about 1991, as the glaciers were receding, they found this person, a couple hikers, and it was near the Italian-Swiss border. And they said, oh, look at this guy. He had a bow and arrow. They said he must be a couple hundred years old. Well, they named him, Otzi or something. It's this, O-T-Z-I. That's the name they gave them. This picture shows where they found him in the Alps, and the picture of what he would look like now is on the lower left. Pretty interesting. As you can see, this thing is pretty well preserved in the glacier. Look at its feet, its toes, its toenails, And then when they tried to recreate him, this is what he looked like, they think. Now, they did the carbon dating, and like I said, a half-life is 5,715 years. And when they did the half-life, they found out that he was not a couple hundred years old. He was 5,200 years old. The oldest sample of a person in good shape that we knew, that anybody found. Okay? Now, if you go on to Google or whatever you go to, look up this guy. It's incredible. He was murdered. They found part of an arrowhead in his back. They know what he ate. 5,200, they know what he ate for his last supper. They knew he was 5 feet 2 inches tall, weighed about 135, extremely muscular. They know everything about him. I think this is one of the coolest finds ever. Okay? But they did the carbon-14 dating on him. And they found out that he was over 5,000 years old. So if you have time, and I mean, you know, we have time since school isn't in yet, look up this guy. And you'll be amazed at what they found out with carbon dating. Okay? All right. Now, next. The next is we're going to do carbon dating again. But this carbon dating happened in our area. This is so cool. So anyhow, in our area in the southern tier of New York, we have the Chemung River. And the Chemung River Chemung is an Indian name. And it means big tusk or big tooth. The Indians gave it that name. Well, why did they give the Chemung River that name, big tusk or big tooth? Because there were a lot of big tusks found when the river would flood a lot around the riverbanks. And they were kind of like an animal like a woolly mammoth. It was called a mastodon. Mastodons are a little bit smaller than woolly mammoths, but they're huge. And what does this have to do with the carbon-14 dating? In 1999, a person near the Elmira College domes was digging up the dirt. It was actually like a bog to make a pond. And the backhoe hit something, and when he brought it up, it was a gigantic bone. And they said, wow, that's pretty interesting. And then there was fur. And so it was almost a complete mastodon. Now, a lot of people don't know the difference between a woolly mammoth and a mastodon. Here, the mastodon is on the right. It's a little bit smaller, a little bit more muscular, less hair, and it's found in this area. And what they wanted to do is they wanted to find out how old it is. So here's what they could have done to find out. Cornell actually did this, but they didn't use these precise numbers, but they came up with the age, which is the same. So here's your next question. Number 2. So, find the age of the mastodon found near the Elmira College domes if a 2-gram sample decayed to 1/2 gram. So, once again, I started out with grams, I gave you grams. So you can use your fingers to find out how many half-lives. Remember, every half-life problem, you got to find out how many half-lives. So, 2 went to 1, 1 went to 1/2. So this had 2 half-lives. So now all we have to do is 2 times 5,715. And that'll give you somewhere around a little bit over 11,000 years. That was close. When Cornell did the half-life, they found out that that mastodon, like a woolly mammoth, was 12,100 years old. And they find mastodons, remember they're like woolly mammoths, around this area. Okay, and there's actually, I think there's a website about Chemung mastodons. That's pretty cool. Okay, now, before we go on, I've got one more, and this was my personal little adventure. I've been scuba diving for about 48 years. I started when I was a junior in high school, like what most of you guys are right now. And we would go to this little place called Little Cayman Island. And I befriended one of the people that lived there, and we'd go diving. And we went diving on some ships that were burnt when there was a battle between some pirates and I think some of the British ships. Now the pirates, you call them buccaneers or privateers or pirates. And we found the ballast stones, which means the stones that they put on the bottom of the ship so it sits upright. And then we were just looking around, and I found these two things. This is a piece of pottery, and this is like, they said, a scabbard for where a knife would go in. And we did this in like the mid-1980s, and I wanted to know the carbon dating. So I went to Miami, but man, it cost too much. I may try to do it maybe next year or whatever, but it just costs too much to carbon date. But the battle took place in like 1630 to 1650, somewhere around there. So it will be very interesting when I finally get those carbon dated to see. Now, we've done 2 questions. There's all sorts of half-life problems. So the next half-life problem, this is number 3. Okay, this is altogether different than those first 2 questions because I don't give you any grams. There's no grams up there at all. So what did I give you that you can figure out? It goes a sample of Ra-226. Ra is radium, like in the last video. And don't forget, Marie Curie found Ra-226 in pitchblende, okay? And it messed them up pretty badly. A sample of Ra-226 decays for 4,800 years. What fraction of the sample remains unchanged? I didn't give you any grams. So it told you how long it decayed. It told you what the element is. And you have to find out what fraction. In other words, is it a half, a fourth, an eighth, a 16th, a 32nd? All right, that's fractions. So you have to figure out which one of those fractions. So if I gave you the element, you immediately know what the half-life is. So if you look here for Ra-226, the half-life is 1,600 years. All right, that's 1,600 years for one half-life. And remember, the first thing you have to find in any half-life problem is how many half-lives. Well, this is not going to be too bad because I gave you what the half-life is. They gave you how long the Ra226 decayed for. So all you have to do is take the half-life and divide it into 4,800 years. That's it. So 4,800 divided by 1,600, 3 half-lives. Now, what do we do with 3 half-lives? Well, I didn't give you a gram number like I said before. It says what fraction. So now you got to go on your fingers. So if it goes 3 half-lives, you start with 1 whole fraction. A whole fraction. 3 half-lives. The whole fraction is cut to a half. Then a fourth. Then an eighth. So your answer is an eighth of the sample remains unchanged. An eighth of the sample. Now, Ra226, their notes and stuff, they had radium all over the place, and their notes are still sealed in a lead-lined box and still radioactive because the half-life is 1,600 years. And think about those poor women, the radium girls that were doing the luminescent dials on the watches in the early 50s. Yeah, this stuff stays around for a long, long time. Long time. So if it doesn't give you a gram number and it says what fraction of the sample, you got to go with 1/2, 1/4, 1/8, 1/16, 1/32. But once again, the first thing you have to find is how many half-lives. Okay. Next. This is really different. This is number 4. Okay, now, why is this different? Because in this problem, I gave you how much we ended up with. So now we have to figure out how much we started out with. Okay? But same thing, find out how many half-lives this thing has. So, find out how many half-lives. Well, first of all, this is what we ended up with. 3 grams, all right? So we have to end up with 3 grams. They gave us the element P32, and they also gave us how many days. How many days it decayed. So what we do is we have to look for phosphorus 32 on here, and it's 14.28 days is the half-life. So, remember what we did before, 14.28 days, we would divide into 57. And so once we divide that into there, we get this. We get 4 half-lives. Okay? Now, we have to do something. That 4 half-lives means we cut the original sample in half, in half, in half, and in half. So we cut the original sample in half 4 times. half, 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 and we got down to 3. So what we have to do is we have to go backwards. Instead of cutting it in half 4 times, we got to double it 4 times. So the first double of 3 is 6. Double that, 12. Double that, 24. Double that, 48. So we started out with 48 grams of P32. That is our answer. So don't forget, if you're looking for the original amount, instead of cutting it in half, you got to double it, double it, double it, double it. Okay? That's a great question. Don't forget, you got to go backwards. And the key is finding how many half-lives. That's the first thing you have to find in every half-life problem. Okay? So, that's how we did that one. Next. Okay. This is, let's see. I think this, I can't remember. I think this is number 5. All right, this is another one that doesn't look anything like the preceding questions. Okay, 8 grams of an element X decays into 1/4 of a gram in 100 years. They want to know what the half-life is. Well, look, remember the first 2 questions we had? I gave you grams we started out with, I give you grams we end up with. So now you can use your fingers. And so 8 grams, the first half-life knocks it down to 4, 2, 1, 1/2, 1/4. So going from 8 to 1/4 of a gram, you have 5 half-lives. And it took, from 8 grams to 1/4 of a gram, it took 100 years. So, how can you figure out what 1 half-life is worth? Easy. 100 divided by 5. So, the answer to this question, 100 divided by 5, 1 half-life is 20 years. One half-life is equal to 20 years. That's a good question too, because they don't give you what element it is. Okay? All right, so that's that one. Next question. This is one of my most favorite questions. Okay? I think this is number 6, I hope. So 40 grams of sample X decays into 5 grams in 15.78 years. So what they want to know is what radioisotope is element X. Okay, now, so we have to find out what radioisotope element X is. Well, look what I gave you. I gave you our starting out mass number and the ending up mass number. So the first thing you can do, fingers again, so 40. How do we go from 40 to 5? The first half-life knocks 40 down to 20, then 10, then 5. So we know that this thing has this, three half-lives, okay? And we know that 3 half-lives, it took 15.78 years. So we have to divide 3. We have to divide 3 in that. So now we know that it took 3 half-lives to go from 40 grams to 5. We got 3 half-lives divided into 15.78 years, and we got 5.26 years. That's the half-life. But this question wants to go further than just finding what 1 half-life is. It wants to know what the radioisotope is. So we look on our little handy-dandy chart for 5.26. And we find out that it's this. The answer is cobalt-60. Cobalt-60 is your answer. Okay, now, I've done quite a few half-life problems. My chem kids, we've done all these problems where it says half-life quiz. What I want you to do now is you are going to do questions on this page. This is 1 to 4. And it goes up to number 11. So, my chem kids, for homework, for you to take a picture of this and your answers. And I want the work on the side. So, you are going to go from 1 to 11. Those are the half-life problems I want you to do. Don't forget, just don't circle the right answer. I want to see your work. Okay? That's half-life. Very cool stuff. Okay.